Thank you very much. Welcome to another session of Everyday Mathematics. At Everyday Mathematics, we do enjoy solving the harder problems. We also see and appreciate the beauty in the simpler problems. Now, today we are still on the MIT 2022 Integration B. We step to the semifinals. Still on this humongous topic of trigonometry. And the first appearance of anything related to trigonometry in the semifinals of 2022 was problem number 2, which was the integration of x to the power 5 times e to the power negative x times sine x, integrating from 0 to infinity. So before I jump onto the solution, a big thank you to our subscribers. We really appreciate your support. We are happy that we are growing. We like to grow this family. But also for those of you who are here for the first time, we encourage you to subscribe to our channel. We will really use your support. For those of you who are here second, third, or fourth time, we really beseech you to trust us on this. We'd like to be on the benefiting end of your support. Thank you once again. And so let's quickly jump into the solution. So this problem looks a little bit complicated. My first instinct in trying to solve this problem is to use Euler's expansion or expression of the sine x function. Sine x is the same as e to the power ix minus e to the power negative ix over 2I, with I being that imaginary number, the unit number in the imaginary domain. So when we substitute that into the integrand, we have x to the power 5 times e to the power negative x times the substitution e to the power ix minus e to the power negative ix over 2I. Next thing is I would want to pull out the constant 1 over 2I and then multiply like terms. So we have the first component, x to the power 5 times e to the power I minus 1 times x. And then the same thing for the second term, which is x to the power 5 times e to the power negative I into brackets 1 plus 1, I plus 1 times x. So we could separate this into two separate integrals, one that encompasses the first exponential function and the one that takes care of the second exponential function. Yeah. Okay, so we have these two integrals, very beautiful integrals. One thing you could see is that these are very similar integrals. The only difference is in the constant next to the x variable, the variable x. For the first integral, the constant is I minus 1. For the second integral, is negative I plus 1. Negative I plus 1. And so I would, one thing that I'm tempted to look at is, okay, so if we have this general integral with a constant x, the constant a, we could use integration by parts, where we have the product here. We take the product of a derivative du dx and then v as our initial integrand. And so first we have the product uv, which in this case is x to the power 5 over a times e to the power ax. Um, we've considered du dx to be e to the power ax such that u integrated is 1 over a times e to the power ax. Then minus, in this case, we have now u, which is 1 over a e to the power ax, times the derivative dv dx, which is 5x to the power 4. So we pulled 5 out already in that case. Then we repeat the process again because this second integral here is very similar to the initial integral, only that now the power belonging to x has shifted from 5 to 4. So we repeat the same process, and here again, we have product of u and v, x to the power 4 over a times e to the power ax minus 4 over a, the integral of x to the power 3 e to the power ax. Again, we repeat the same process over again. And here we're driving towards eliminating the x component so that we're left with just e to the power ax. So as you see here, we've gone down to x squared. Keeping on the process, going down, at this point, we've moved from 3 over ax squared e to the power ax, and the product uv is x squared over a times e to the power ax, minus 2 over a, the integral of x times e to the power ax. Repeating the process with these, finally we arrive at a point where we have only the exponential function there, and that can easily be integrated. So you see we have nested functions here. As you can see, lastly here, we just have to integrate e to the power ax, which is obviously 1 over a e to the power ax. Now we want to remove these intermediate brackets so that we have one single expression. So we have x to the power 5 over a minus all these other components, which results into, so here at the very end we have e to the power ax over a squared, but as it propagates upwards, we have 120 over a to the power 6. So now with the intermediate terms here, we have from the beginning, we have x to the power 5 over a times e to the power ax. 5 here, 5 times x to the power 4. So we have 5 over a squared times e to the power ax. Now this 5 times 4 here, and negative times negative, we have a positive, so which is 20 over a to the power 3 x cubed e to the power ax. Now since there's a plus here, times this negative remains a negative, but we have 5 times 4, which is 20, 20 times 3, which is 60. So 60 to the power over a to the power 4, because we have a times a squared times this a cubed, and this a to the power 4. So we have minus 60 over a to the power 4 x squared times e to the power ax, plus, then we have this, since at this point we have a negative times this negative becomes positive. So we have 1 60 up to here times this 2, we have 120. 120 over a to the power 5 times x, e times e to the power x. And then lastly, since at this point we have a plus times a negative is a negative. And since we don't have any other constant except 1 here, it remains 120 times 1, which is 120 over a to the power 6 e to the power x. Now, so looking at these, it's very interesting that for both our integrals, since the limit of any power of x times e to the power plus or minus I, since this is an oscillating function, minus -1 times x tends to 0. Why? Because this e to the power negative x component here tends to 0 when x becomes a very big number. And so 0 times any number here becomes 0. The same thing as x tends to 0 because we have an x here that goes to 0. So essentially, if we have these two integrals here, it means that the intermediary terms, and by intermediary, we're talking about those with the x component will tend to 0 at both the upper and the lower limit. So we are left with the only terms at the end. So, which means that since we had a negative 120 over a to the power 6 times e to the power ax, since we have this negative here, when we multiply that negative with the negative of the last constant, it becomes positive. So we have a flipped situation here. So we have 120 over a here is negative I plus 1. So we put that in bracket to the power 6 times e to the power negative I plus 1 the power times x minus 120 over this a constant I minus 1, which is the other constant, to the power 6 times e to the power I minus 1 x. And then we have to take into consideration the limits. As you can see, at the upper limit, as x tends to infinity, this tends to 0, this tends to 0. At when x tends to 0, this e to the power component tends to 1, and so we are left with that. So essentially, our integral now becomes, since we're only taking into consideration the lower limit, we now have to flip this because of upper minus lower. So we have now 120 over 2i, and then we have I minus 1 to the power 6 minus 1 over negative 1 plus I plus 1 to the power 6. So how do we solve these very high numbers? We can use de Moivre's theorem. De Moivre's theorem states that first of all, we have to convert these complex numbers into a constant, and then we have the cosine and the sine component. As you can see, I minus 1 to the power 6, we can pull root 2 out, negative root 2, and we're left with 1 over root 2 minus I times 1 over root 2. This is the same as negative 2 to the power 6 is the same as 8. And then here we have e to the power negative I over pi over 4, because this is cosine pi over 4 is 1 over root 2, sine pi over 4 is 1 over root 2. So as you can see, there's a negative sign here, so we can take that to the numerator. And then when we multiply by 6, the same as pi over 4 times 6, which is 3 over 2 pi. And so cosine of 3 over 2 pi is 0, and sine of 3 over 2 pi is negative 1 times this I, we have negative I over 8. The same thing for this, we can pull root 2 out, and then we have negative root 2 to the power 6, that's same as 8. We have 1 over root 2, 1 over root 2, which is e to the power I, pi over 4, power 6, times the power 6, that becomes 3 over 2 pi, and when we take this into the numerator, it becomes a negative, and so negative times the negative 1, sine of 3 over 2 pi is negative 1, becomes a positive, so we have I over 8 as our answer. So this integral in totality now just involves obviously subtracting the second term from the previous term. And since for this we say the answer was negative I over 8, and then for this it's the same as positive I over 8, negative minus this becomes 1 over 20, 2I times negative 2I over 8. This 2I and this 2I cancel, so we have the answer being negative 120 over 8, which is negative 15. So this is our answer. It's not very complicated, but obviously initially the problem looked a little bit intimidating, but it just takes knowledge of De Moivre theorem. But even there, you didn't need to use De Moivre theorem entirely. You just needed to know how to take advantage of Euler's expression, combining the e to the power negative x and the e to the power ix from the sine function. And then you'll be able to solve it. Anyway, thank you so much for hanging out with us today. It's been really, really nice solving this problem. Until next time, please subscribe to our channel. But I'm looking forward to solving the next problem. Bye-bye.